Welcome to this practical on pulmonary function tests. The aim of this practical lecture is to give a basic overview and some information on two specific lung function tests, and then also how to obtain these tests and how to interpret the values and the graphs received from these tests, and more information on specific measurements that can be made and the diagnostic value of these measurements. There are a variety of lung function tests which can be used for a range of purposes to test specific lung functionality. But the specific two lung function tests that we will be focusing on for the purpose of this practical is the spirogram and the flow volume curve. So the spirogram measures lung volumes and lung capacities. So because there's no time involvement or no time dependent measurements being taken by the spirogram, we say that the measurements being taken by the spirogram are static. However, the flow volume curve measures volume and flow rate. So flow rate refers to the speed of the flow of air. So this tells us that time is involved in these measurements, and therefore measurements taken by the flow volume curve are considered to be dynamic. Okay, so let's start off from the very start. So when a patient has been informed that they need to go for a lung function test, it's very important that they are informed before going for the test. So in other words, whilst they're making their appointment to go for the test, that a few things need to be avoided. So they need to be instructed that they need to avoid wearing restrictive clothing when they go for the test. They need to avoid smoking before the test. They need to avoid alcohol within 4 hours of the test. Vigorous exercise needs to be avoided within 30 minutes before the test. And ingestion of a heavy meal needs to be avoided within 2 hours of testing. Then also both short-acting and long-acting bronchodilators has to be avoided before the testing. The instrument that is used in order to obtain a spirogram and a flow volume curve is called a spirometer. Now, attached to the spirometer is a detachable mouthpiece. So it's very important that when doing these lung function tests that you make sure that you have taken a mouthpiece from a sealed package. It is not recommended ever to reuse a mouthpiece, as many pathogens can get trapped inside the mouthpiece. So always make sure that the mouthpiece that is used is taken from a sealed packet and never to reuse a mouthpiece. Daily, before the use of the spirometer for lung function test, it's important that the instrument is calibrated. This is only necessary once per day. So if the spirometer is used throughout the day, if it was calibrated once in the morning, that would be sufficient. Now, the equipment needed for this calibration includes a 3-liter calibration syringe. You do also get 1-liter calibration syringes, but we use a 3-liter calibration syringe. And then you also need a hygrometer, barometer, and thermometer. Because we need to enter the relative humidity, the height above sea level, and the room temperature. And all of these ambient conditions, they need to be entered into the software before calibration takes place. During the preparation of the subject or the patient, prior to the lung function test, it's important that you as the clinician provides a few pointers on exactly what is expected of them throughout the test. So it needs to be explained to them that throughout the test they need to remain in an upright position with their head elevated. So this is vital because this ensures that the chest cavity is open and that air can flow freely without obstruction. It's also important to tell them that when placing the mouthpiece into their mouth, they have to put their teeth over the mouthpiece first and then seal with their lips. It's also important to apply a nose clip to prevent air from escaping through the nose. And then it's also important for you to ensure that the patient is in a comfortable and relaxed position. In order to obtain a reproducible and reliable lung function result, it's very important that the maneuver is explained to the patient beforehand. So the patient needs to be adequately prepared before doing the test so that they understand exactly what to do for the duration of the test. So in order to obtain a spirogram, the instructions to the patient would be the following. They would be instructed to perform slowly and completely the following movements. So first of all, they start by breathing normally for a few breaths. This is then followed by a maximal inspiration, followed by a complete exhalation. So the key to obtaining a spirogram is that the patient breathes normally. There's no forced maneuver taking place. The spirogram basically consists of normal breaths and then a maximal inspiration and a complete exhalation. And after the adequate performance of this maneuver, the resulting spirogram looks like this. So we need to remember that the spirogram measurements are only volumes and capacities, not any time-dependent measurements are being taken. So volume is being measured on the y-axis. So any rising parts of the diagram would indicate an increase in volume, and any falling parts of the graph indicate a decrease in the volume as read off of the y-axis. So now we'll take a closer look at the different volumes that can be measured with a spirogram. So if we think back to the maneuver that was explained to the patient in order to obtain the spirogram, the first instruction to the patient was that they needed to breathe normally. So they needed to perform normal inhalations and exhalations. And this is demonstrated in the graph as these smaller waves, an inhalation and an exhalation. Normal inhalation, normal exhalation. So this volume of air that's represented by this normal in and exhalation is called the tidal volume. And the tidal volume is usually estimated at around about 0.5 liters or 500 milliliters. Now, the next instruction to the patient was to perform a maximal inspiration. So the maximal inspiration would take place over here. So during this part of the maneuver, during maximal inspiration, this would represent the patient's inspiratory reserve volume. So in other words, that would be the volume that the patient has to inspire after a normal inhalation. And this is usually about 3.3 liters. Now, the next part of the maneuver, the patient was instructed to exhale completely. So that would be after normal exhalation, the exhalation which takes place even further, and that represents the expiratory reserve volume. So in other words, the reserve that you have to expire after a normal exhalation. And this volume is usually about 1 liter. Now, even after maximal expiration, there is still a certain amount of volume which remains within the lungs, which cannot be exhaled. And this is a very vital volume because it's this volume that remains in the lungs even after maximal expiration that prevents the alveoli from collapsing. And this volume is called the residual volume. And it's described as the amount of air left in the lungs after maximal expiration. And the residual volume is usually about 1.2 liters. Okay, so after looking at the static volumes which can be measured by means of the spirogram, we now move on to look at the different capacities which can be measured with a spirogram. Remember, these capacities are still static because it is time independent. Now, the definition of a capacity is the sum of two or more volumes. So the first capacity we look at is the inspiratory capacity. So the inspiratory capacity is described as the capacity of your lungs to take air in. So it's the total capacity that your lungs have to take air in. And if we look at the volumes which are summed to add up to the inspiratory capacity, it includes the inspiratory reserve volume as well as the tidal volume. So in other words, those two volumes make up the inspiratory capacity, which is an indication of how much air the lungs can take in at any time. The next capacity is called the functional residual capacity, and this capacity is the sum of the expiratory reserve volume and the residual volume. So the functional residual capacity describes the volume of air that's left in your lungs after a quiet exhalation. The next capacity we look at is called vital capacity. The vital capacity is the sum of the inspiratory reserve volume, the tidal volume, and the expiratory reserve volume. So basically, the vital capacity refers to all of the air that can get into and out of the lungs. So in other words, it refers to the volume or the absolute volume of air which your lungs have to work with. Now, besides certain pathological conditions which can influence this vital capacity of the lungs, there are certain general factors which influence the vital capacity. And these general factors include age. So vital capacity generally decreases with age. Gender is another factor which influences the vital capacity. Males generally have an increased capacity compared to females. The general build of a person also influences vital capacity. Someone who is taller and has a larger chest size obviously has more capacity for the lungs to expand, meaning that their vital capacity will be higher. The strength of muscles, and here we specifically are talking about the respiratory muscles. So if these muscles are more developed, such as in swimmers or martial arts performers or deep sea divers, or even musicians which play wind instruments, which constantly are strengthening and developing these respiratory muscles, they also have an increased vital capacity. Other factors such as race also influence the vital capacity. And then also elevation above sea level. So people generally living at higher elevations above sea level have to continuously breathe deeper because the air that high above sea level has lower oxygen concentration. So this constantly having to breathe deeper increases their vital capacity. And the last capacity we look at is total lung capacity. So total lung capacity is a sum of all four the volumes. So the inspiratory reserve volume, the tidal volume, the expiratory reserve volume, and the residual volume. That is your total lung capacity. So it's all of the volumes added together, the total volume your lungs can hold, not just the volume that can be breathed in and out. Remember, there's a difference. The volume of air that can be breathed in and out is the vital capacity, but the total volume that your lungs can hold is the total lung capacity. The maneuver to obtain the flow volume curve is quite different from getting a spirogram, because if you remember from the maneuver that was performed in order to get the spirogram, slow and complete breaths were taken, so there was no forcing taking place. But with a flow volume curve, this is a forced maneuver. So in other words, the air has to be pushed or forced out during exhalation if you want to get proper results. Now this slide explains the first of the two maneuvers. So in order to obtain a flow volume curve, there are two different types of maneuvers depending on the software which has been installed with the spirometer. So for maneuver 1, the patient is instructed to place their teeth over the mouthpiece and then seal with the lips. They are then instructed to breathe normally for 4 breaths, so 4 relaxed breaths. From here, they then have to inhale as deep as possible, so in other words, a maximal inspiration. And then this is where the main difference comes in the maneuvers. They are then instructed to forcefully and quickly exhale. So this is not just a complete exhalation, this is a forced exhalation. And this exhalation is also timed, so the software actually tells the patient when to stop exhaling. So the machine makes a beeping noise, and that beeping noise is indicative of the end of the exhalation. After this forceful exhalation, they then inhale one more time as deep as possible. After adequately performing maneuver 1, the flow volume curve that is obtained looks like this. Remember that the measurements that are taken by the flow volume curve include both lung volumes as well as flow rate. So flow rate tells us that speed is a factor. So the rate or the speed at which the airflow is taking place is an important factor during this lung function test. And now we see that the axes of these flow volume curves differ quite a lot to that of the spirogram. So volume has now moved to the x-axis. So volume is measured on the x-axis, which was previously on the spirogram that was measured on the y-axis. And now flow rate in liters per second is measured on the y-axis. As you can see, the y-axis is split into two. So there's a positive and a negative part of the graph. I just want you to understand that just because there's a positive and a negative part of the graph doesn't mean that a negative amount of air can be inhaled. The change in symbol from positive to negative on these two different sides of the y-axis is just to indicate that the airflow is taking place in different directions. So one part of the graph is going to represent exhalation and one part of the graph is going to represent inhalation, meaning that the flow of air is taking place in two different directions, and therefore we have positive and negative flow rate in liters per second. However, when you answer a question asking the flow rate, you never add the negative sign. Okay, so now we're going to go through the different parts of the maneuver that the patient is instructed to perform and exactly how the flow volume curve is drawn during the maneuver or is obtained during the maneuver. So if you remember what the first instruction was to the patient was instructed to breathe normally for 4 breaths. So during normal breathing, the patient breathes normal. So there's breath 1 in and out, breath 2 in and out, breath 3 in and out, and the last breath, breath 4 in and out. After this, the patient was instructed to inhale deeply. So this is the deep inhalation, maximal inhalation. This is followed by forceful expiration. Forceful expiration, remember this continues until the beep. So the patient hears the beep, and then this is followed by the final inhalation. Okay, now we'll take the flow volume curve and we will look at the different volumes that can be obtained when analyzing this curve. So first of all, the bottom part of the graph, if you can remember, this was drawn during inspiration. So as the graph was busy taking place, so normal breathing was taking place over here, 4 normal breaths, 2, 3, 4, and then inhalation. So every time inhalation or inspiration was taking place, this was done during the bottom part of the curve, so below the x-axis. So everything happening below the x-axis, that represents inspiration, whereas everything above the x-axis represents expiration, because remember, as normal breaths were taking place during the small circle over here, then there was inspiration. This was followed by the forceful and quick expiration until the beep. So anything that happens above the x-axis represents expiration. Now, normal breath or normal breathing was taking place during this part of the graph. So that means that that part of the graph represents the tidal volume. Remember the volume that is inhaled and exhaled during normal breathing. So that little circle represents the tidal volume. And that is about 0.7 liters in this case, because if this is 2.5 over here and this is 3.2 over here, then it means that this volume is about 0.7, because remember, volume is being measured on the x-axis, so we are looking at the x-axis going this way, so the volume would be 0.7. Now, since inspiration is taking place at the bottom of the graph and the direction of inspiration was going this way, it means that the part from 0 to 2.5 represents the inspiratory reserve volume. So the volume left to inspire after normal inspiration. And that is, in this case, rate off of this graph is about 2.5 liters. Remember, because it's also read on the x-axis because it's a volume. And since expiration was taking place in this direction, this area would represent the expiratory reserve volume. In this case, it would be about 1.8, because remember we said this is 3.2. So the difference between 3.2 and 5 gives us 1.8 liters. Once again, it's a volume, so we're reading it off of the x-axis. And then all three of these volumes summed together give us the forced vital capacity. So this corresponds to the spirogram where the inspiratory reserve volume plus the tidal volume plus the expiratory reserve volume gave us the vital capacity. But in this case, there's just an F in front of it because now we refer to this capacity as a forced vital capacity, because the maneuver used to obtain the flow volume curve is a forced maneuver. And the forced vital capacity is about 5 liters because it's this entire volume on the x-axis. So now let's quickly compare the volumes obtained from the spirogram versus that of the flow volume curve, specifically those volumes that correspond between the two. So the tidal volume on the spirogram was represented by the small waves, whereas tidal wave on the flow volume curve is represented by this circle in the middle of the curve. The inspiratory reserve volume of the spirogram moves upwards because volume is measured on the y-axis. So an inspiratory reserve volume would indicate an increase in the volume and therefore move upwards. So that's the inspiratory reserve volume on the spirogram. But volume is being measured on the x-axis for the flow volume curve. So therefore the inspiratory reserve volume would be the difference between 0 and 2.5 because inspiration, remember, was moving in this direction. For the spirogram, the expiratory reserve volume would go down because once again, volume is being measured on the y-axis, so a decrease in the volume during expiration is represented by a downward wave from the tidal volume because it's the amount of air being exhaled after a normal exhalation. And for the flow volume curve, once again, it's being measured on the x-axis. So expiratory reserve volume is represented by this part over here because expiration was moving in this direction. So that's just the difference between how the volumes are read off of these two different lung function curves. And then, of course, vital capacity is the sum of all three of these volumes. So on the spirogram, that would be in the vertical plane this way, but the flow volume curve, it would be on the horizontal plane, and in this case it's now referred to as the forced vital capacity because of the forced maneuver. A very important diagnostic value can be obtained from the flow volume curve, and this is called the forced expiratory volume percentage, or FEV percentage. So how this works is from the start of exhalation. So while the patient is exhaling, so remember that's this part of the graph at the top. So from the start of exhalation, the software starts to time. And after 1 second of exhalation, a mark is made. And this little green line represents the mark. So a mark is made, and that mark is referred to as the FEV1. So FEV1 stands for the forced expiratory volume after 1 second. So basically what FEV1 is it tells us how much air is being exhaled after 1 second of exhalation. So of the total of 5 liters of air, a total of 4 liters was exhaled during 1 second of exhalation. So in order to determine the FEV percentage, we use this equation. We say FEV percentage is equal to the FEV1, so the volume of air that was exhaled after 1 second, divided by the total volume of air multiplied by 100. And in this case, it was 4 liters of air that was being exhaled after 1 second from the total of 5 liters of air multiplied by 100. That gives us 80%. And a normal FEV percentage is 80% or above. If the FEV percentage is lower than 80%, it could be indicative of a pathology such as asthma, bronchitis, emphysema, etc. So basically we want that FEV percentage to be 80% or more. So in other words, the patient should be able to exhale 80% of the total amount of air within 1 second of exhalation. Okay, so here's another example of determining the FEV percentage. So let's just get our equation first. So remember, FEV percentage is FEV1 divided by FVC. So here's the mark that the machine has made after 1 second of exhalation. And that means, so that's our FEV1, and that means that 3 liters of air was exhaled. So if we plug that into our equation, we have 3, because that's our FEV1, divided by 5, which is our forced vital capacity. So our FEV percentage is 60%. So this is below the 80%, which means that this could be indicative of a pathological condition within this patient. So it indicates a problem. Besides FEV percentage, a few other important values can also be obtained from the flow volume curve, and that includes the peak expiratory flow rate and the peak inspiratory flow rate. So while we look at the y-axis, so we are looking at the flow in liters per second, we need to always remember that the top part of the curve represents the expiration and the bottom part of the curve represents inspiration. So if we make a line through the very top of the expiration curve, that is our peak expiratory flow rate. So our PEFR, our peak expiratory flow rate, which makes sense because this is at the peak of the expiration curve. And because we are reading this value off of the y-axis, it means that the unit for this value will be in liters per second. So the peak expiratory flow rate of this curve is 10 liters per second. Very important to remember the units. Okay, and to the same end, if we draw a line across the peak, so the highest point or the peak of the inspiration curve, that is where we find the peak inspiratory flow rate. And the peak inspiratory flow rate on this graph is 8 liters per second. Remember, because we were reading off of the y-axis. Note that it's 8 liters per second and not minus 8 liters per second. Remember, we said that the minus sign just shows a change in direction from expiration to inspiration. This is just a summary of all of the different volumes and the different flow rates that can be obtained from a flow volume curve. So these are the instructions for maneuver 2. So maneuver 2 is a little bit different from maneuver 1, but both of these maneuvers help us to obtain a flow volume curve. So the instructions would be that the patient needs to empty their lungs completely. They then place their teeth over the mouthpiece. Remember, teeth first and then seal with lips. Firstly, they need to inhale as deep as possible, filling up the lungs, so it's a maximal inspiration, and then once again a forceful and quick exhalation. And they carry on until the beep is heard, just like with the maneuver 1, and then afterwards there's a deep inhalation and then removal of the mouthpiece. So when going through the steps in this maneuver, we notice that the difference between maneuver 1 and maneuver 2 is that in the case of maneuver 2, the patient was not instructed to breathe normally for those first 4 breaths. So there's an immediate inhalation, a forceful exhalation, and then end off with another inhalation. Okay, so now we look at the difference of how the flow volume curve is constructed when the patient performs maneuver 2. So the curve does look a little bit different because the maneuver does differ. So in this case, for maneuver 2, the patient was instructed to inhale deeply and then forceful and quick exhalation. This exhalation also continues until the beep is heard, and then this is followed by a final inhalation. So basically we see that the circles that we started off with for maneuver 1 are not there because in this case the patient was not instructed to breathe normally for 4 breaths. So therefore it's basically just the outside border of the curve that exists. So if we look at the differences between the flow volume curve which is obtained by performing maneuver 1 and the flow volume curve obtained from performing maneuver 2, we see the clear difference is basically in this central part, that the maneuver 2 does not have the central part. So that means that essentially the values that can be gained from the flow volume curve obtained through maneuver 2 is the peak expiratory flow rate, the peak inspiratory flow rate, and the forced vital capacity. The tidal volume, the inspiratory reserve volume, and the expiratory reserve volume cannot be read off the flow volume curve obtained from maneuver 2, since we don't have the tidal volume which is being measured. And then of course FEV percentage can also be determined off of maneuver 2 because the software still makes a mark after 1 second, so that's our FEV1, and then we can determine the FEV percentage by dividing the FEV1 through the forced vital capacity. When performing this lung function test on a patient, 3 acceptable maneuvers are required, and these 3 acceptable maneuvers also need to be repeatable. And the repeatability criteria means that these 3 acceptable maneuvers have to be within 5% of each other. Specifically, the FEV percentage and the FEV1 need to be within 5% of each other. So the variability between the 3 maneuvers that were performed cannot be higher than 5%. Otherwise, these maneuvers are not then accepted as acceptable maneuvers. These flow volume curves are just a few examples of poor maneuvers that were performed. So we can see that in this graph, the patient started off with a very nice forceful exhalation, but then obviously stopped abruptly before the beep. So we can see that that was what happened there. In this maneuver, we can see that there was a hesitant start, there was a slow start, so the forceful expiration didn't take place from the beginning. It was a bit hesitant. On this graph over here, we see that during the inspiratory side, there was an early termination, could be caused by a cough. And in the last graph over here, we see that during the expiratory phase, there was firstly a slow rise, a slow start. So we also see that the peak isn't as high as it could be, so the force in the beginning of the exhalation was not adequate, and then also we see some erratic breathing, could be caused by coughing or phlegm, etc. Now we move on to a few abnormalities, specifically referring to lung function abnormalities. So abnormalities are divided into two main streams. So you have restrictive abnormalities and obstructive abnormalities. So we start off by looking at the restrictive abnormalities. So restrictive pathologies or restrictive abnormalities are things that restrict the lungs from expanding and filling up maximally. So in other words, what we're saying is that during restrictive diseases or restrictive pathologies, there's a decrease in the lung volumes because the lungs are physically being restricted from expanding to their maximum volume. And examples of this include pregnancy, obesity, and tight-fitted clothing such as corset. So all three of these, or the first three examples, refer to a physical decrease in the space that is available for the lungs to expand. So during pregnancy, obviously there's much less space for the lungs to expand because the expanded uterus is taking up so much space. In obesity, the adipose tissue that's surrounding the organs actually causes restriction and then takes up some of the space, causing the lungs not to be able to expand maximally. And then obviously wearing tight-fitted clothing. For instance, in the olden days, they used to wear corsets and they pull them very tightly around the chest area. That would restrict the rib cage from expanding, and therefore the lungs cannot expand maximally. So these first three examples basically referring to a decrease in space. The next three examples, fibrosis, asbestosis, and silicosis, basically refers to diseases that are associated with industry. So these diseases cause the lungs to be less compliant, and there's physical changes in the lung tissue, which means that they can't expand maximally. So fibrosis, specifically, we are talking about pulmonary fibrosis. So that's where there is scarring of the lung tissue, which is usually caused by pollutants or dust or chemicals. So there's scarring of the tissue and change of the lung tissue itself. Asbestosis occurs when there's breathing in of asbestos fibers, and silicosis is when there is silica dust deposits that are being deposited in the lungs. So as we said, these three bottom examples are associated with industry. So physical alteration in the lung tissue itself, which restricts the lung from expanding maximally and thereby decreasing the lung volumes that can be inhaled. And we said that restrictive diseases cause a decrease in the lung volume. So if we look at what it does to the lung volume curve, we see that there is a clear decrease in the lung volume. Remember, because in the flow volume curve, volume is being measured on the x-axis. So a decrease in volume, which means that you end up with an elongated curve. You can see that there's a clear decrease in the volume. So if we look at a spirogram, the volumes in general would decrease, but that would be on the y-axis, because for a spirogram, the y-axis represents the volume. So a decrease in volume would mean that all of the graphs move down. So the volumes of the graphs are less, and that would be indicative of a restrictive disorder. Next, we look at the obstructive abnormalities. And obstructive diseases are then further subdivided into large airway obstructions and small airway obstructions. So we start off by looking at large airway obstructions. So this is defined as any obstruction between the vocal cords and the segmental bronchi. So between the vocal cords and the segmental bronchi. So any obstruction taking place in this area over here is considered to be a large airway obstruction. Now, if there is obstruction, this decreases the flow rate, because obviously if there's something that's hindering, obstructing the air that's flowing in and out of the lungs, it means that the flow rate is going to decrease. And examples of this are tumors, so tracheal tumors, foreign objects that could be lodged within the trachea, or tracheal lesions. And if we look at the flow volume curves that are then formed in or for a patient with an obstructive disorder, we can clearly see that the flow volume curve has been reduced to this blob-like structure. And that makes sense because we said that obstructive disorders influence the flow rate. And remember, flow rate is measured on the y-axis. So if there's a decrease in the flow rate because of this foreign object or the tumor that's obstructing the flow, it means that there will be a decrease in the graph size on the y-axis, thereby reducing the graph to this blob-like structure. The next category of obstructive disorders are small airway obstructive disorders. So these are obstructions that limit the flow in the airways which are less or smaller than 2 millimeters in diameter. So 2 millimeters in diameter is already a very small area. So if that is decreased or obstructed by something else, it means that there's basically no space left for the air to move out. And a typical example of small airway obstruction is chronic obstructive pulmonary disorders such as chronic bronchitis and emphysema. So in chronic bronchitis, we see that these bronchial tubes become inflamed and then they secrete this thick layer of mucus. We can see the thick layer of mucus, and this thick layer of mucus then further obstructs the airflow through these small diameter pathways. In emphysema, we can see a clear damage to the air sacs or the alveoli. There's disintegration of the septums. So the air basically gets trapped in these alveoli. Now, people with chronic obstructive pulmonary disorders have an increase in their residual volume. And this makes sense because the volume actually gets trapped within these small airways. So the residual volume, remember when we looked at the spirogram, is that volume that remains in the lungs even after maximal exhalation. So for people with COPD, that volume increases even further because the air is getting trapped in these small airways. Two more examples of small airway obstructions is asthma. So during asthma, you can see that you also have this inflamed and narrowed pathway, so it makes it difficult for the air to move in and out of the lungs. And then also cystic fibrosis. So important to know the difference between cystic fibrosis and pulmonary fibrosis. Cystic fibrosis is an inherited disorder which causes this thickened mucus to form and cover and fill the alveoli. So this mucus then blocks the airways and also causes damage to the lungs. And if we look at the effect of small airway obstructions on the flow volume curve, we see that a small airway obstruction causes an incoving of the flow volume curve. So initially, the peak doesn't look too affected. There's still a little bit of a peak, but so telling us that the initial part of the exhalation is okay because the initial air obviously is coming from the larger airways. But as the air starts to get exhaled later during the exhalation process, when that air is actually coming from the small airways, then we can see that there's an incoving because of the obstruction taking place. So here we see the incoving taking place, and if we look at the spirogram, we can see the increase in the residual volume in the spirogram because of the air that's getting trapped and the inability to exhale that air. And as a summary, or as the last slide, just a comparison of the different flow volume curves. So the blue curve representing a normal flow volume curve, where you can see a very nice peak expiratory flow rate and a nice shape in the curve. The green curve representing a restrictive disorder because we have a decrease in the lung volume. And then the red curve showing us the small airway obstruction because there's an incoving during the latter part of the exhalation, and the purple curve representing a large airway obstruction because there's overall decrease in the flow rate because of something that is literally obstructing the air from flowing into and out of the lungs.